So now we want to find the center of mass of a uniform rod. And we have the result for a continuous body, which is an integral over the body of dm r to that mass element dm divided by an integral of dm. Now our goal is to figure out how to apply this result specifically to real physical objects. And the key, as always, is choosing a coordinate system. So now I'll draw the object again. And the first thing I'll do is choose an origin. I can pick my origin anywhere I want. I could pick it in the middle. I could put it in the middle. I could put it at this end. I could put it at that end. I could put it down here. But I'll choose it over here. Because the object is linear, this is a very Cartesian system, I'm only doing a one-dimensional object. So I choose my coordinate system plus x. That's step one. Now, my origin. Now, here comes the crucial thing. In this argument, dm is the infinitesimal mass element. And I want to pick that at an arbitrary place in the object. I don't want to pick it at the origin. I don't want to pick it at the end. Note down here, this is x equals L. So I'll arbitrarily pick an infinitesimal element. I'll shade it in dm. That represents, this is what I'm going to make my summation over when I do my integral. I'm going to add up all these dm's. And the point is that the dm's are different distances from the origin. So the vector, and here's the next step, is I draw a picture of my vector r dm. So now I have these terms at least explained in my diagram. The next step is to introduce an integration variable for both of these quantities. So step one was the coordinate system. Step two was the identification of dm. And step three, and I think this is absolutely the crucial one, is to introduce the integration variable. Now, you'll see that will come in two different places. So this is the quantity, the distance from dm to the origin that's changing. You can see for each of these little elements, that changes. So what I'll write dm as a vector is x prime, which will be my integration variable in the I hat direction. So the integration variable is x prime. That's the first place that I introduce the integration variable. And x prime, you can see, will vary. And it varies from x prime equals 0 to x prime equals L. And that will show up in terms of the limits of my integral. Now, the second place that the integration variable comes in is dm. I want to express dm in terms of x prime, which is a measure of where this object is. And that's how, if we choose this length here to be dx prime, notice in terms of the integration variable, then I have a relationship between dm and dx prime. dm is mass in this little element. dx prime is the length of the element. And if the whole object is a uniform rod with a mass capital M and a length L, then it's just given by m over L dx prime. And this quantity, m over L, is an example of a mass, linear mass density, which we have a skill challenge about. So I have two places where my integration variable has been introduced. And now I can write up every piece in this integral. So let's now indicate that we're integrating from x prime equals 0 to x prime equals L. dm is m over L dx prime. And our vector is x prime I hat. And downstairs, it's just m over L dx prime from x prime equals 0 to x prime equals L. And that's how I set up the integral for the center of mass. Both of these integrals are now not difficult to do. Notice it's x prime dx prime. So this integral is x squared over 2. And I get 1/2 m over L, L squared. And downstairs, dx prime from 0 to L is just L. So the downstairs integral is just m over L. And when you have m over L's cancel, we just are left with this is just m, not m over L, dimensionally incorrect. So we get, for the position of the center of mass, the m's cancel, one of the l's cancel, and we have an I hat in this expression. So our answer is r equals L over 2 I hat, which is exactly what we expected. We expected the center of mass to be halfway down the rod.